Hello everyone, thank you for listening. My name is Yu Lai and I'm from China. Now I'm a PhD student of Hong Kong Baptist University. I received my master degree from Shanghai Tech University in 2024. This work about graph neural network on heterophilic graphs was done in Shanghai Tech. Let's start by introducing graphs. A graph is a data structure used to represent relationships between entities, consisting of nodes and edges. Graph machine learning tasks include graph node classification, link prediction, and so on. We introduce graph homophily here, which represents the tendency of nodes of the same class to connect with each other in a graph. The higher the graph homophily is, the more nodes tend to connect with those of the same class. A common used measure is the proportion of edges that connect the nodes of the same class out of all edges. Previous research has referred to graphs with edge homophily above 0.7 as homophily graphs and those below 0.7 as heterophilic graphs. We list some examples of homophilic and heterophilic graph here. The top left is a social network, and the top right is a plotting function of networks. And the left button is a hyperlink graphs, and the right button is the brain graphs, which are heterophilic. Graph neural networks have made significant breakthroughs in graph machine learning tasks. Traditional graph neural networks are based on a message passing mechanism, which includes two parts, aggregations and transformation. Aggregation is to pass node features along the edges of graph, and the transformation is to use linear or nonlinear mapping to produce the output of message passing. Traditional message passing based GNN are based on homophilik assumption, which means that the adjacent nodes on the graph tend to belong to the same class. With non-negative aggregation weights, adjacent nodes end up having similar representations, when adjacent nodes belong to the same class. This approach works naturally well. However, when the adjacent nodes are likely belong to different classes, it can lead to nodes of different classes having similar representations, as shown in the table at the bottom right. Based on the node features, MLP outperforms GCN on heterophilic graphs, like Wisconsin and Texas. To address the shortcoming of traditional GNNs, many GNNs are designed for heterophilic graphs. Firstly, they can use multiple neighbors in aggregation. Secondly, we can use signed weights in aggregation to distinguish the nodes from the same class and the different classes. Thirdly, and most importantly, we can use topology explicitly. Traditional GNNs aggregate node features via graph topology, implicitly encode the graph structure. However, some research has found that explicitly encoding the graph topology by directly use linear layers or MLPs to reduce the dimensionality of the adjacent matrix as the input GNNs can lead to better performance on heterophilic graphs. Notable examples include links and glow GNN. But directly using adjacency vectors as GNN's input results in large model computation costs and difficult to optimize. If we explicitly encode topology via MLP or linear layer, the parameters to be learned will be very large. The direct idea is to reduce the topology dimension before training. Another observation is that multi-order adjacent matrix AM can be helpful to the node classification on heterophilic graphs. As shown in the right figure, we concatenate the multiple adjacent matrices as the input of a linear layer here. We find that the model with higher order topology information achieve better performance. Based on the facts, an efficient embedding method for high order topology is needed to improve learning model performance. After getting the topology embedding, we need to integrate the topology into GNNs. More precisely is to combine the topology-based model with GNNs with different architecture adaptively. We do the following observations. Firstly, we find the confidence and the accuracy of GNNs and topology-based models on a set of heterofleet graph nodes are positively correlated. In other words, models have higher accuracy with more confidence, and vice versa. Secondly, as shown in the picture here, we also find that GNNs and the topology-based model can be with different accuracy on different classes, which can be considered as a fact to combine these two models. For the first observation, we proposed a novel and efficient embedding method, being of path embedding. We firstly do the power of A, and the elements in A M represents the amount of passes with certain length M between any pair of nodes. Nodes V1 to Vn are divided into D groups with the same size according to their index. For example, the V1 and the 2 Vn subscribe D are in the first bin, and so on. Then we sum the column of adjacent matrices with different powers by the bin of passes here. However, simply summing up the column of adjacent matrices may make nodes from different classes with similar topology representations. We further consider the position information of the power A. We get index matrix here, whose elements are the subscription of non-zero elements in AM. We then sum up the columns of the index matrix and do normalization to the position matrix. After that, we do the weighted sum of matrix B and the position matrix here for different power of A, and finally concatenate them to get the final embedding. In order to make better use of the obtained graph embedding, we designed a flexible graph neural network algorithm, BOP-GNN. BOP-GNN consists of an MLP called BOPNet and an arbitrary graph neural network GNN. As shown in this figure, BOPNet takes the graph embedding obtained by BOP as input to predict the node class. We denote the output of the last layer of GNN and BOPNet as HBOP and HGN here, and we'll do the weighted sum to get a final prediction. BOP-GN use a mechanism called confidence and class-wise accuracy-based combination to weigh the HGN and HBOP to get the final prediction. Firstly, the confidence of BOPNet and GN on each node we can get, and the training accuracy of the predicted class of BOPNet and GN on each node are obtained during training process. Then the importance theta of BOPNet and GN is calculated by this equation here, which takes the product of BOPNet class-wise accuracy and confidence as the numerator and the GNs as the denominator. After that, we can get a final prediction by weighting HBOP and HGN by the importance of value theta. Here is our experimental results, and we use heterofleet graphs with different size. The largest heterofleet graph is snap patterns with 200 million nodes and 1300 to 2 million nodes and 13 million edges here. We compare different baseline models with our BOP-GN, including linear classifiers, conventional GNs, and heterofleet GNs. The BOP-GN models achieve the best performance on almost every heterofleet graph dataset. Both GAT attained highest scores on Square, Chameleon, Snap patterns, and Archive. Both GloGeon ranked first for Twitch camera node classification. Let's analyze the results of GAT and Bob GAT. We find that the performance enhanced of GN over GAT correlated with the level of graph conflict. The lower the conflict is, the greater the improvement. This could be because when conflict is lower, the representation of nodes of different classes become more similar using the assumption of graph conflict. And thus, high-quality graph topology plays a significant role in distinguishing nodes of different classes for graph neural networks. The improvements of BobGN for Link and GloGN were smaller. This might be due to the fact that Links and GloGN already explicitly encode the first-order original graph topology and have far more parameters than BobNet, making optimization more difficult. To further verify the applicability of BobGN to other graph neural networks, we compare the GCN2 and the H2GCN with their respectively Bob-enhanced versions. It can be seen that BobGN effectively improves the classification accuracy of these graph neural networks on heteroglyph graphs. In the ablation study, using BobGAT as an example, we validated the effectiveness of different components of BobGN. We firstly compared the classification accuracy of GAT, BobNet, and BobGAT. We found that BobNet has higher accuracy than GAT on all datasets, and BobGAT overall performed BobNet. This indicates that although BobNet overall performed better than GAT performed better on certain nodes, and BobGAT cleverly combines the advantages of both GAT and BobNet through CCAW. Firstly, we use the row adjacent matrix as input, and when the row adjacent matrix was used as input, BobGAT performed poorly, possibly due to two reasons. That is high cost computation cost, and is hard to optimize. During graph embedding, we limit the highest order number to 1. We find that similar to using the row adjacent matrix, leaking information from higher node order neighbors during graph embedding negatively impacts BobGAT performance. We removed the positional embedding encoding from Bob, and we find the performance decreases because the positional information is lost. We also replace our embedding method with different other embedding methods like TSVD and random projection and so on. We find our embedding is better than the other embeddings. We recorded the node classification accuracy for each class of BobGAT of different classes. The X represents different classes of the datasets, and the Y-axis represents the testset node classification accuracy. We find that BobGAT can perform better than multilink and GAT and combine their accuracy. Then we do the cumulative distribution of CCAW weight vector on different classes, and we find that when the weight is larger than 1, the BobNet is more important, and when the weight is smaller than 1, the GN performs better. Lastly, we analyze the efficiency of Bob and the BobGN. We analyze the CPU runtime for obtaining graph embedding on snap patterns. It shows that Bob requires about 100 seconds, wherever other embedding methods like RONE and TSVD require 1,000 to 10,000 seconds. The growth rate of Bob overhead is much slower than the other two embedding methods. On snap patterns, analysis of model accuracy, training speed, inference speed, and the max GPU memory usage shows that BobaGN performs better compared to GN, with additional overhead being acceptable. We can see that although BobaNet encodes multiple adjacent metrics while Link only encodes a single adjacent matrix, BobaNet is still faster, smaller, and more accurate. Compared to multi-link, BobaNet achieves the inference acceleration of 18.8 times with a 6% accuracy increase, and its memory consumption is only 0.16 of that of multi-link. By reducing the input dimension, we have reduced the parameter count of topology-based models, accelerated computation, and lowered the difficulty of training. For both GAT, they consume slightly more computational resources by GAT, but considering that over GAT accuracy improves by 25%, such additional costs are acceptable. Finally, we'll get to the future works. Some future work we can introduce here is, firstly, the data augmentation for heterophilic graphs can be done, like graph classification to removing redundant edges, and do dataset distillation to generate representative small graphs. Secondly, we can do more tasks and settings on heterophilic graph like link prediction and unsupervised learning. And lastly, we can do research on heterophy of different kinds complex graphs like dynamic graph, hypergraph, and so on. Thank you for your listening. That's all. Thank you.